Now let's take a look at an absorption spectrum. You can see the absorption spectrum is being shown here in black, and you have your usual sort of shapes. Now you also see that we have a couple of, there we are, a couple of little bands right here, here, and here. Some narrow peaks hiding inside of that spectrum. Now why is that? Well, that kind of tells us that we have something that's going to have some pretty defined transitions, right? Just like we expect for atomic spectroscopy. And we still see some of that here in molecular spectroscopy. So, if we come back over to an energy level diagram, this will be our ground state. This will be our first excited state. But we also know there's going to be some vibrational levels on top of those electronic transitions. That's just all about how much heat energy it has and how much vibration it's capable of doing when it relaxes. Now, if I go for the lowest transition, so I go straight from the very bottom, there we are, from the very bottom spot to here, it's going to be the smallest amount of energy that I have, which means it's going to be the farthest toward the red wavelength. Now, if I go up to a higher energy level, so if I go up to the first vibrational state, but I started out in the bottom vibrational state, that's going to be a bigger transition as well. And so that's going to have more energy, and we're going to shift to the blue side a little bit. And you can see that what we're doing is we're always starting from the ground state down here, which makes sense because we're going to be thermally relaxed. Now that said, I'll say, if we have enough heat for what we're doing our measurement with, we may have the first state more significantly populated, maybe even the second vibrational state more significantly populated. And so we'd have a combination of these bands that we see here, plus the same things coming up from the first vibrational state, and the ones coming from the second vibrational state. So we'd have a much more complicated absorption spectrum, which is more common actually, and that's one of the reasons we often just see broader bands than this. Okay, but let's just stay with this simpler example for a moment. You can see here that we have a bunch of little peaks that we'd expect to see heading toward, from the red end toward the blue end. Sure enough, we see one's going from the red end toward the blue end. It's probably not terribly shocking to us that this one happens to be the biggest one either, because if we're starting out down here in the bottom state, this is the one that's easiest to get up to. Now that doesn't mean it's always going to look like that. You're going to have lots of times where the biggest peak is not the lowest energy, but you know, it makes some sense when we're talking about a system that's designed to be quite so simple. You might look at this molecule and say that is not very simple, but keep in mind the incredible amount of pi conjugation that we have here. And so we have a giant molecular orbital over this entire molecule, and so it's acting a lot more like you'd expect for atomic spectroscopy as a result. Now when we come over to the emission side, well, keep in mind what happened first on the absorption side. Yes, it absorbed this and we observed the absorption, and then what did it do? It's going to relax to that ground state, right? Well, to the ground vibrational state of the first electronically excited state. That's a better way to say it. There we are. So everything is thermally relaxed to this state. So we start out with all of our electrons currently residing in this specific band. So when they start to relax, what's the biggest energy transition they're going to have? Hey look, it's the exact same amount of energy as we had right there. And so they usually call that lambda 0. And you can see here the band for lambda 0 for absorption and emission are going to be very close together, like you'd expect. In fact, you might have expected them to be identical, and we'll talk about why they aren't identical in just a moment. But, okay, we expect them to be really, really close together. And then I'm expecting that my next one, to the first vibrational state, that one should be lower in energy still. Next one should be lower in energy, lower, lower. And so we expect to see the exact same sets of bands, in a lot of ways, extending out this direction. Now, of course, the gaps up here may not be the same size as the gaps down here, so it may not be a perfect mirror image. But if you needed to do a quick and dirty sketch, and you said, this is my excitation spectrum, you'd probably guess that your emission spectrum is going to look something like this. It's at least a good starting point when you're thinking about it. Now, I also want to point out something, though. There's a little extra feature happening there, and to be honest, I'm not exactly sure what's happening there. That's not a common thing. I do know what's happening right there, but either way, what I'll point out is that these are separate processes that aren't part of our normal fluorescence process. So our rule does still stand, that we're still going to have a nice smooth behavior on this side. It's just that there are other behaviors that are also happening. And they can result in some of these sort of additional bands that you see there. But what's up with that gap between the transitions? Why are they slightly different? Well, here's one spot where we've turned a little bit myopic. We're talking about this molecule, but we're talking about this molecule like it's in a vacuum. Don't forget that it's being surrounded by a bunch of solvent molecules. And when it's around the solvent molecules, it's going to be rearranging them by depositing heat energy into them. And also, it's going to have to move around a little bit too, because as you change the shape of the molecular orbital around this, some of these bond angles are going to change a little bit. Now, here's an example of that going for a much more simple molecule. Now, for you to use VSEPR, hopefully you remember that from general chemistry, using VSEPR, we would have said, okay, I've got an electron group there, I've got an electron group here, and I've got an electron group here. Since there's 3 electron groups, I'm expecting that formaldehyde is going to have, initially at least, a 120-degree bond angle between each of these bonds. But then we remind ourselves, oh, but that double bond is big. The electrons kind of extend out this direction and this direction. As a result, it's going to squeeze this down a little bit. So now we're going to say this is going to be greater than 120. Same thing down here. This is going to be less than 120. We might have ballparked that and guessed probably about like 116. And sure enough, we end up having it with a bond angle of about 116.5 degrees. Now that's for the S0 state. Now when we excite one of the electrons into an excited state, the S1, we have something a little more interesting happening. What we've actually done is we've actually created an extra region of space where the electrons are starting to spend some time. And it's almost like the whole molecule is starting to change into some sort of a tetrahedral geometry. So you can kind of picture that there's a set of orbitals up here that's starting to get more populated more often. This dotted line is just showing the plane that we started with originally, and that the oxygen is bent 31 degrees out of the plane of the paper now, going downward. It's not showing that there's actually an extra bond here or anything. It's just saying that, this is where we started with. It's down 31 degrees. The bond is also lengthened. We're at 132 picometers. And so all the energy involved in that rearrangement is going to be partially responsible for having the emission spectrum start out lower. So keep that in mind. We actually have this molecule rearranging in space, and that also means that it has to push some solvent molecules away. It has to form like a little bit of a cavity for itself, burrowing around inside of these water molecules or whatever it's dissolved in. And that's one of the sources of that Stokes shift, is what we call this. The difference between our 2 initial wavelengths that we'd expect.